We have Yu-Jye, who will be giving a talk on obfuscation. Please give him your attention throughout the entire talk. Thank you.
Well, hi everyone. Thank you for coming to my talk on an effective approach to software obfuscation. So before we get to the main idea, which is the idea of how to effectively implement obfuscation, let us first understand what software obfuscation is. So, what is software obfuscation? Software obfuscation is a software protection mechanism that is performed through program transformation. And this transformation has two main side effects. First, it makes the corresponding executable binary more difficult to analyze. And second, is that it performs that first step without changing program's core functionalities. So, this definition is still very textbook-like, so we can break it down a little bit more. What do we mean by more difficult to analyze? And this difficult aspect is actually made up of three distinct properties: potency, resonance, and stealth. And Christian Kohlberg is actually the first person that used those three properties to assess the quality of an obfuscation transformation or obfuscation technique. So what are these three properties then? So on one hand, potency is a measure the strength of the transformation against automated analysis. And automated analysis as in a person sitting in front of a computer like myself, actively trying to figure out how to undo the transformation with traditional tooling like a disassembler such as Redot2, IDAPro, Ghidra, Binary Ninja, that can take an executable in 0 and 1 and display its content in human-readable form. And usually that human-readable form entails the instruction that's contained within the executable binary, and usually we call that the disassembly, and also the data that the instruction use. So besides the disassembler, another popular tool is also the debugger, such as GDB, that can take a snippet of disassembly, that can help an analyst verify a snippet of disassembly, and verify as in verify the runtime behavior. So, the stronger the potency, the harder it is for an analyst to understand the disassembly that is displayed by a disassembler, or to verify the runtime behavior with the help of a debugger. And on the other hand, resonance measures the strength of the transformation against automated analysis. And automated analysis is just like myself again, sitting in front of a computer, press a button, and boom, the transformation is undone. And some example automated analysis tools are Anger, BingSeg, BAP, and B2R2. And actually, in particular, BingSeg has the capability to undo a transformation called Opaque Predicates. And BingSeg is basically a terminal program. Underlined in blue is the command you type to a terminal to invoke BingSeg on an executable binary called anagram_OLVM. And underlined in yellow is basically the output from BingSeg where it actually accurately identifies the opaque predicates in that executable binary. And lastly, stealth. Stealth measures the strength of the transformation against initial detection. So essentially, it's just how well the transformed code blends in with the original authentic code. So the stronger the stealth property, the harder it is to differentiate between the transformed code and the original code. So with the knowledge that, So one big distinction that I must make is that software obfuscation is not the same as cryptography. The protection offered by software obfuscation does not have the same mathematical guarantees as cryptography. So for example, we cannot make statements such as, it will take 2,000 years of a 2.2 single core CPU to undo the said transformation. In other words, the strength of the transformation, three properties that we just discussed earlier, the strength of each one can be reduced. So, with the knowledge that we can never make it computationally impossible in one's lifetime to undo obfuscation transformation, the one that we know now, or the one that we might discover in the future. Perhaps there's a better or more precise term for what we meant by more difficult to analyze. And really that precise term is time-consuming. Essentially, we can only hope to make an obfuscation technique more time-consuming for an analyst to undo. So ultimately, the transformation's three properties that made up this time-consuming aspect combine to answer the question of how much more time-consuming did this transformation make it for reverse engineering. At the end of the day, we really just want to make the analyst gives up. And software obfuscation achieves this not by making the information that it protects impossible to uncover. Software obfuscation achieves this by making the process of uncovering this information so time-consuming that the analyst eventually gives up. So now the question is, how do we maximize this time-consuming aspect? And to answer that, let's look at the deobfuscation process. Because really, this generic deobfuscation process actually maps really well to the three properties that we just discussed earlier. So for deobfuscation, usually the first step is that we want to identify the obfuscation technique. And the ability for an analyst to perform this step really depends on the stealth property. So the stronger the stealth property, the harder it is to perform this step. And after we identify the obfuscation technique, now then we can perform the relevant deobfuscation step. And the ability for an analyst to perform this step really depends on the potency and resonance property. So the stronger the potency and resonance, the harder it is to perform this second step. And if we look at modern obfuscation technique, really what we see is that they only focus on the second step of the deobfuscation process. So they only focus on making the potency and resonance property stronger, while giving little to no regards on the stealth property. In summary, modern obfuscation are noisy, and they're noisy because they are easy to identify, and the root cause of that is really because they have low stealth. So let's take a look at an example of a modern obfuscation technique called control flow graph flattening. So before we get to the theory of how this obfuscation technique works, let us first understand what a control flow graph, or abbreviated CFG, is. So a CFG is a representation of a function disassembly where the program flow is also encoded. And how it's able to encode program flow into its representation is that it represents disassembly in basic blocks and use arrows connecting to different basic blocks to represent the control flow. And a basic block basically has one unique entrance point and one unique exit point. So once you enter a basic block, you will always execute the same sequence of instruction. So this means that if the disassembly contains like a control flow ordering instruction, like an if statement, then the disassembly in the CFG representation will be split into multiple basic blocks as shown in this picture here. So in this picture, the top basic block ends with an if statement, and if the if statement evaluates to true, it will go to the basic block at where the green arrows is pointing. And if it evaluates to false, it will go to the basic block where the red arrow is pointing. So why is this representation useful then? Well, in this representation, it actually increases a disassembly's glance value, with the ability to quickly glance over the disassembly and have some sort of understanding of what the code is doing. And to be more precise, one can recognize high-level programming construct, such as the if statement, as explained earlier, while loop, for loop, and also switch statement, by just a quick glance of the disassembly. So what this particular obfuscation technique do is that it removes the increased glance value that this CFG representation provides, such as the shape indicating high-level programming construct, as discussed earlier, and also just any type of inference that an analyst can make by just how close the basic block is to one another. And how it's able to do so is that it transforms every possible control flow graph, an example shown to the left, into the into the one shown to the right. And how it's able to do so is that it takes each original basic block from the original CFG, flatten at the bottom of the new CFG, and then it adds a dispatcher that chooses which original CFG to go to. So essentially, post-obfuscation by this particular transformation will make every control flow graph look like this. So why does this have low stealth? Well, that's because all the transformed CFG will have that particular distinctive shape. So modern obfuscation is noisy. They are easy to identify because they have low stealth. But does it matter? It shouldn't matter if the deobfuscation process still takes a long time, right? Well, the problem with that way of thinking is that real-world implementation leaves behind very distinctive footprint to allow for tool-specific or non-generic approach to deobfuscation. Let's take a look at OLVM implementation of control flow graph flattening. So OLVM is a publicly available obfuscator that you can just find on GitHub. So an example transform code by OLVM is shown in that particular CFG. So in OLVM, an original basic block will always end up with setting the same local variable to a constant that tells the dispatcher what's the next original basic block that it should execute next. This means that once we figure out the constant that corresponds to each of the original basic block that's flattened at the bottom, then that allows us to just quickly reconstruct the original CFG. So what's the solution? How do we effectively implement obfuscation then? Well, instead of focusing on making the obfuscation technique harder to break, also focus on making it harder to identify. So instead of just focus on this potency and resonance property, don't forget the stealth property. Respect each property that makes up this time-consuming aspect. And perhaps to drive the importance of this stealth property even more, it might be better for us to also think of it on a higher level. What's more frustrating? Understanding what the problem is, but not how to solve it? Well, with the availability of the World Wide Web, there's bound to be solutions online that solve similar problems. So learn the general approach to tackle those problems and use it to tackle the one you have at hand. How about not understanding or even aware of what the problem is? Well, in that case, it's really not anything I can do, right? So if an analyst is not aware of what is obfuscated, it makes that person make the wrong assumption about what the code is doing. And once you make the wrong assumption, it also makes them fall deeper into this rabbit hole. And in the context of reverse engineering, we usually call that the reversing hell, which is spending days, weeks, hopefully not months, but probably, of analyzing the same executable binary without understanding anything about what the internal is, how the internal is implemented. And really, out of the three properties that make up this time-consuming aspect, only the stealth property can achieve this idea of making the analyst make the wrong assumption about what the code is doing. So to end this talk, I will give a more concrete example on the importance of this stealth property. So recently, I was studying an obfuscation technique called Opaque Predicate. And during my research, I discovered the assumption that IDA Pro makes when it tries to automatically identify opaque predicate. And I was able to utilize that assumption to make stealthy opaque predicate when it's analyzed under IDA Pro. So just a little background, opaque predicates belongs to disassembly desynchronization. And disassembly desynchronization is basically an umbrella term for obfuscation technique whose main goal is to degrade the accuracy of the retrieved disassembly. So what do I mean by an inaccurate disassembly then? Well, an inaccurate disassembly is basically a disassembly that contains code that will never be executed during program runtime. And here's an example shown here. The first instruction is basically an if statement. And if this if statement evaluates to true, the execution will go to where the arrow is pointing. So it will start executing the add instruction and then the decrement instruction. But if the if statement evaluates to false, it will go to an instruction right after the if statement, which is the move instruction. But this particular if statement during runtime will actually always evaluate to false. But the disassembler does not know that, so it still disassembles the code at where the arrow is pointing, or the byte at where the arrow is pointing as code instruction, thus inaccurate disassembly. So, what's opaque predicates? Opaque predicates is basically just that. There are conditional branches that always evaluate to true or false. This means that one of the branch is always unreachable at program runtime, so jump bytes or random data bytes that are not meant to be parsed as code instruction can be inserted. And in this particular opaque predicate shown here, which is kind of like in a CFG representation, this particular opaque predicate contains a predicate that will always evaluate to true. This means that you can put jump byte at the false branch. So other than IDOT-Pro, there are also other tools that will try to automatically identify opaque predicates that include BSidesSF and also a binary ninja plugin called Opaque Predicate Patcher. And the way they work is that at every basically if statement, they will ask the question of, can both branch be executed? And if the answer is no, or if they can determine that the answer is no, then they know that an opaque predicate exists. But the problem with that approach is that opaque predicate, well, the predicate itself, depending on how it's constructed, determining that property or being able to answer that question is non-trivial. So, since identifying opaque predicate is hard, IDOT-Pro takes a heuristic-based approach to identify them instead. And here's IDOT heuristic. If IDOT-Pro detects overlap instruction in sibling basic block, it will always assume that the conditional branch is an opaque predicate. So what do I mean by sibling basic block? Well, in the picture shown here, basic block basic block B and basic block C are sibling because they originate from the same if statement. And what do I mean by overlap instruction? Overlap instruction are when one or more instruction bytes are interpreted as more than one instruction. So for the opaque predicates here, if the if statement evaluates to true, then the byte 31, C0, D1, C8 will be parsed as an XOR and OR instruction. But if it evaluates to false, those same 4 bytes will be evaluated as a move instruction. So here's where IDA makes an incorrect assumption. If it detects that structure I just discussed earlier, basically overlap instruction in sibling basic block, it will always assume that the jump byte is placed in the false branch. But there's really no stopping for the jump byte to place in the true branch instead. And let's look at a more concrete example here. So in this disassembly, the second instruction is basically the if statement. And if the if statement evaluates to true, it will go to the instruction at where the not jump label is. So it will start executing the XOR and OR instruction. And just to explain the disassembly a little bit, those two instructions, XOR and OR, essentially sets EAX to 0. And EAX is the return value. So on a higher level, this function will return 0. As shown by this disassembly. But if we look at the false branch, which is the instruction that follows the J and Z, or the if statement, essentially, that instruction is not disassembled. It's just left as a data byte, B8. So it's just left as a raw data byte. Why didn't IDA disassemble that? Well, IDA detected that structure we discussed earlier, basically overlapping instruction in sibling basic block. And remember, once IDA detects that structure, it will always assume the jump byte to be placed in the false branch. So essentially what happened is that IDA basically believed that the B8 data byte is a jump byte and not an instruction byte. But for our example, the junk byte is actually placed in the true branch instead. So this means that the XOR and OR instruction will actually never be executed. They are the junk byte. And the real instruction actually starts there. So the instruction should actually be parsed at where the B8 data byte is. And if we disassemble from there, we see that what's really will be executed during program runtime is that EAX register will be assigned a non-zero value. So essentially, instead of returning 0, this function will actually return a non-zero value. So remember how previously I said how this opaque predicate is stealthier? Well, how is it stealthier? Well, here we're able to achieve 3 things. First, we make IDA display the wrong instruction, the XOR and OR. Second, we make IDA not disassemble the authentic instruction. And third, we make IDA not show any sign of distress on that there's some problem going on with the disassembly. So before IDA implemented this particular heuristic to detect opaque predicates, if there's overlap instruction, IDA will highlight certain part of the disassembly in red to let the user know or the analyst know that something is wrong. But since here IDA believes that it successfully detected opaque predicate, it does not do that type of highlighting at all. So it shows 0 sign of distress to the analyst. So in summary, really when trying to implement obfuscation, try to respect each property that makes up this time-consuming aspect. And right now, really the focus has only been on the potency and resonance property, but we should really also focus on the stealth property because it is also equally as important. Thank you. I guess any question?
How does the earlier example look like in the control flow graph that IDA outputs?
Oh yeah.
So the question was, how does the earlier example look like on the flow graph?
Oh, we're showing IDA? Actually, to be honest, I don't remember, but if IDA detects any, sorry, say again?
Does it not even show the other branch exists?
Actually, yeah, it will show not the other branches. That's what I would assume too, because IDA believe that that's actually correct disassembly. So the control flow graph would just be, probably just be one branch pointing to the other. But I actually don't remember, so I can't say that for sure. So,
Any other questions?
okay, thanks.
Just gonna open it up.
Excuse me, just one more question for you.
Okay.
You said there was opaque predicate patchers. Do they work when the predicate itself relies on variables that are unknown, or do you have to feed it known state for it to be able to determine that something is opaque?
Oh yeah, so for that particular plugin, actually by the Binary Ninja disassembler, they can do this more advanced program analysis technique called value set analysis, which is basically the ability to, like, for a register, they will try to determine all the value in that register. So for that particular plugin, if it determines that the register that the if statement depends on always evaluate to the same value, then it will basically know that it's an opaque predicate. But if it can't determine that, then it doesn't. So let's just say if the construction of the predicate is through, like, because I know that, and they actually talk about the limitation. And so the limitation, so basically how well that tool works is based on how well the value set analysis is. So, and certain limitation is basically, if I remember correctly, if the predicate depends on, like, is it maybe memory, like on the heap, like they won't do certain analysis if the predicate is constructed in a certain way. So,
Sorry, one more question if you don't mind.
Oh, yeah, go for it.
For IDA, if the junk jump goes to a location that doesn't overlap with any other functions, will IDA pick up that that is a opaque predicate, or does it have to overlap?
So yeah, for IDA's case, it does have to overlap. So in a way, IDA heuristic is it's incomplete per se. So it's an incomplete implementation to detect opaque predicates. So, Thank you.